Good morning and welcome to TEC 293 for Thursday, February 11th. Today we're going to start talking about a brand new topic in this class, and that is tensile testing. For example, I have this specimen of aluminum, and I have this piece of oak right here, and I have several different pieces of plastic right here, like this. And basically what we're going to do is we're going to put these different specimens into a machine, and we're going to pull them apart. We're going to stretch them until they break. And in the process, we are going to measure how much they stretch and how much force it takes to do that. And we'll see when they fail and how they fail as well. So it's pretty fun. I really enjoy this section of the class because we can start breaking some stuff. All right, but before we start talking about that, let's take a look at the schedule. So I have that in front of me. And don't forget that we have Lab 3 due tonight by 11:55 p.m. That's hardness testing. And due by 11:55 p.m. tonight. So if you look at the schedule, today is tensile testing of materials part 1. So that's going to be kind of the basic fundamentals of tensile testing. We're going to talk about how we do the test and some things like stress and strain and ultimate tensile strength, which we looked up before for lab 1, but we haven't really talked much about it since. And elastic modulus and ductility. And some other terms as well. So we're going to start talking about all of that stuff today because it's all relevant to tensile testing of materials and other tests that we'll do later on in this class as well. All right, so that's what we're going to do today. And then next time on February 16th, we'll finish up the discussion of the fundamentals of tensile testing. And we'll talk about how to apply this stuff into problems, solving calculation problems. Like I have this piece of aluminum and I want to know how much force can it take before it breaks. And so we can do some calculations and we can solve a bunch of different problems given the basic parameters that we understand about aluminum based on our tests. So we'll talk about all of that next time, and we'll talk about how we can solve some calculation problems with the data that we acquire from these tests next time. All right, and that is pretty much all leading up to lab number 4, which is the first tensile testing lab. In lab number 4, we're going to do tensile testing just of the plastic components, the plastic specimens. And when we do that, it takes a little bit longer than lab 3. So what I'm going to do is divide the groups into 2 days. So I'll have some of the groups come in to do lab 4 on February 18th. And the rest of the groups to come in to do lab 4 on February 23rd. So more details about that in the near future, but I will divide the groups into 2 days so that we have some more time to get familiar with the process and the machine that we use for the next several labs. Because then lab 5 is very similar to lab 4, but we do on different materials. Lab 5 will do tensile testing on wood specimens and on metal specimens. And then lab 6 is actually really similar as well. We're going to talk about compression testing, which is really just the opposite of tensile testing. If you do compression testing, you're just squishing the specimen together. You're squishing the specimen instead of stretching it apart. So it's really just the opposite, and it has a lot of similarities to tensile testing. All right, and that's most of what we're going to do in the next couple of weeks. So that's the schedule. We're building you up to be able to do labs 4 and lab 5 especially, and then lab 6 is just kind of a special case of that. All right, lab 4, 5, and 6 are pretty fun because you get to start breaking some stuff, and you get to start using the Instron UTM, Universal Testing Machine, down there in the lab, which is that big, tall machine you probably saw in lab 3 when you were here in person. And it's a big, very capable machine. Costs about $150,000 if you were to buy it from Instron directly. And it's a pretty cool piece of equipment that we're kind of fortunate to have in our lab. So that's what we're going to do in the next couple of weeks. So let's go ahead and get started talking about tensile testing. Okay, so let's get started talking about tensile testing. What we're going to talk about first are some nomenclature and some terms related to tensile testing. We'll review the concepts of stress and strain, which are really important for tensile testing, as well as compressive testing that we'll do in a couple of weeks. There's a new term that's called the modulus of elasticity, also known as the Young's modulus, that is really important when talking about tensile testing. And then we'll talk about some other effects like toe compensation, and we'll talk about what ductile and brittle materials look like when you do tensile testing on them. We'll talk about toughness and true versus engineering stress. Those last four things are just kind of some extra things that are important to think about as we're doing tensile testing. So first of all, how are we going to do tensile testing? Well, I've mentioned this before, but it's slightly counterintuitive. What you might nominally think you would do to do tensile testing is maybe hang a specimen from a support structure and then increasingly apply load to it, apply force to it, and see how much it stretches. But that is not the way we typically do tensile testing. That's not the standard ASTM way of doing tensile testing. The way tensile testing works is you put a specimen inside these jaws, right here and right here, and then what the machine does is gradually pull it apart, gradually stretch it apart at a fixed rate, and you can change that, you can set that, whether it's half an inch per minute or 1 inch per minute or 1.27 inches per minute, whatever, we can change that. And it depends a little bit on the specimen, but it is specified by the ASTM instruction. So what we have is a moving crosshead. This is what moves to stretch the part. We have a load cell. This is what actually measures the amount of force, and then that gets reported to the computer, which is going to log that data. And then we have the test specimen itself, and then of course we have these grips that are going to have to grab the specimen and hold it in place as it's being stretched. So I want to relate this back to Lab 2 because there's a reason why we did Lab 2. It seems kind of silly maybe that we're doing a lab on springs, but I probably mentioned this at the time. The reason why we do Lab 2 on springs is because, to a certain extent, every material in the world behaves like a spring, up to a certain point, which is to say that if I take this specimen and I pull on it up to a certain point and then I let go, it will return to its initial position. It behaves like a spring. That's what a spring does, right? If I pull on it and then I let go, it returns to its initial position. Also, with a spring, we saw in Lab 2 that we can relate the amount of force exerted by the specimen to the deformation of the specimen, right? And once you found the spring constant, K, you were able to relate the amount of force exerted by the spring to the amount of deformation of the spring, right? So you can do the exact same thing with any materials in a certain region of tensile testing. And we'll talk more about that in just a little bit. But that's why we do Lab 2, is because every material that we're going to test, that you could test, behaves to a certain extent exactly like a spring. All right, so now I've said most of this up here. So the spring constant, here's really the only thing that I haven't said yet. The spring constant, K, when we relate that to tensile testing of a material, it's not called the spring constant anymore, but it's basically the same thing. But in a material that we're going to test, we call that spring constant, we call it the elastic modulus, sometimes called the Young's modulus, sometimes called the modulus of elasticity. They all mean the same thing. Unfortunately, there's 3 different words to mean the same thing, but you notice they all have the word modulus in them. So if you're talking about tensile testing and you see the word modulus, it refers to one of these things. All right, the symbol to abbreviate this is always capital E. That's the symbol for the elastic modulus of the material. All right, so here's basically how tensile testing is going to work. We have the testing procedure. It's saved in the computer. And I have programmed the computer with the specific constants like how fast it's going to stretch and a few other like preloading conditions, things like that, that aren't really that important for you to know. But the important thing for you to know is that you're controlling the test with the computer and the appropriate procedure following the ASTM instructions are programmed in there. So you can find the ASTM instructions, just look online and you can find them. So the UTM, the Instron machine, is going to stretch the specimen at a predetermined rate. Most of our tests are going to be between about a half an inch per minute to about 1 inch per minute, something in that ballpark. And then what happens is our machine is electric. It's driven by electricity, and it has a motor down at the base, and that motor spins a screw. It's kind of like a worm gear drive. So that motor spins a screw, and that moving crosshead is attached to that screw, and as the screw rotates, that moves the moving crosshead up or down. And so the machine knows the position of the moving crosshead by determining how many times that screw is rotated around. So it's counting the rotations of that screw that's rotating around, driven by the motor in the base of the machine. And by counting the rotations, it knows where the moving crosshead is, and it knows how much the part has stretched. All right, and then, so that's the extension or the stretch data. The other important piece is the amount of force that we're getting in the part, and that is measured by what's called the load cell, which is sending its information to the computer, and the computer is recording the amount of load or the amount of force being exerted by the part. All right, so the way we're controlling this test, in other words, the independent variable, is actually the stretch of the part, the stretch. Meanwhile, the dependent variable, the result, is the force. And we're going to convert those to strain and stress, respectively, in just a little bit. But for now, it should make sense that the independent variable is the stretch, and the dependent variable is the resulting force or load on the part. All right, so that's the raw data that you're going to get. When you do lab 4 and 5 and 6, the raw data, the file, is going to be an Excel file, and it's going to give you a column, actually 3 columns. One column is going to be time, which you don't really care about. The next column, I don't remember which order they're going to be, but the next column is going to be force, like in pounds force, and the next column is going to be deformation or stretch, which is going to be measured in inches. All right, so using that, you could get the so-called spring constant, just like we did for the springs in lab 2. But when you think about that, just consider how the spring constant is going to be different for these materials. All right, so here's a much smaller specimen. Here's a much larger specimen. Would you expect these to have the same spring constant? Probably not, because this one is much bigger and thicker. So it's going to take a lot more extension to get a certain amount of force, or vice versa. It would take a lot more force to get a certain extension in this part than it would in this part, right? So when we have a relationship between force and stretch, that is an extrinsic variable. That's extrinsic, because it depends on how big your part is, how big your specimen is. Same thing over here. This is a much thicker part, this is a much thinner part. And so if I was to apply a certain amount of stretch to this part, I would expect a much higher force than if I applied the same stretch to this part. Or vice versa, if I applied a certain amount of force to this part, I would expect a lot more stretch than if I applied that same force to this part. All right, so even though these could be the same materials, they look a little bit different, so maybe they're not. But these could be the same materials. Suppose these were both aluminum and these were both brass or something, doesn't matter. They're both the same material, but because they're different sizes, you would get a different spring constant, right? And that's usually not desirable. If we're trying to characterize a material because we want to use that material to turn around and design a structural support beam for a building, or design a chassis for a car or something, or an aerospace application, we want intrinsic data. We want intrinsic characteristics of the material. That way it doesn't depend on what size and shape and thickness my part is. All right, so we want to make this into intrinsic data. And there's a way to do that. This is what I've just said. We want intrinsic properties, not extrinsic properties. And so what we have to do is make two transformations. We're going to make a transformation to the stretch, and we're going to make a transformation to the force that we're measuring on the UTM. And you're going to have to do this in Lab 4 and Lab 5 and Lab 6. Remember, you're going to get a column that has the force, and you're going to get a column of data that has the stretch of the part. And you're going to have to create two new columns. One column you're going to do a calculation on the force, and one column you're going to do a calculation on the stretch. The first one is we're going to convert all of those force data points into stress. And if you remember, the definition of stress is force divided by area, force per unit area. So what you're going to do is if you're testing this part right here, and the machine gives you a certain amount of force, this is how much force is being applied at that certain point in time, what you're going to want to do is convert that force into stress by dividing the force by the cross-sectional area. So to get that, you'll have to know the radius or the diameter of this test section right here. And we'll talk about that. You'll know that. But that's what you're going to have to do, is create a new data column for these next few labs where you convert all of the force data points into stress. And generally in this class, we're going to be using English or freedom units, whatever you want to call them. And we're going to be using PSI, pounds per square inch. So you'll get the force data in pounds, force, and you'll have to divide by the cross-sectional area, like you took a slice right here, the cross-sectional area of the specimen. So that's one of the transformations that you'll have to do. That gives us an intrinsic variable, whereas force is extrinsic, stress is intrinsic. And similarly, we're going to convert the stretch of the specimen to strain. And the strain is this Greek letter epsilon. This was sigma, by the way, lowercase Greek letter sigma. This is lowercase Greek letter epsilon. It looks kind of like a backwards 3. And what that is equal to is the change in length, which is the stretch of the part, divided by the original length of the part. So what was the original length? What was the change in length? And dividing the change in length divided by the original length, that gives us the strain of the part. One more thing to mention here, when we talk about the original length, what we're talking about on this specimen is actually what's called the gauge length. And the gauge length is this test section of the material. So when we do this part right here, what's going to happen is the grips are going to grip on right here and right here. And these sections here and here, these aren't really going to stretch very much at all. Number one, because that's what's being gripped by the machine. But number two, because these are so much thicker in cross-section than this section of the part. So what we refer to as the original length here is actually going to be the length of this narrow section from here to here. And when we measure the change in length, we're going to measure the change in length also of this gauge length section, the test section right here. All right. We'll talk a little bit more about that in the future, but I want to give you a heads up on that. All right, so initially when you get your data from lab 4, 5, and even 6, 6 is compressive testing, but it's going to be very, very similar. Your data is going to be load in pounds force. That is your dependent variable, so it should be on the vertical axis. And your independent variable is the stretch or displacement measured in inches. So that would be on the horizontal axis. So this is the data as you get it from the instron. But like we said just a few minutes ago, this is extrinsic data. because the actual amount of force here, this amount of force, it depends on the size of the part. If I have a much bigger part, then it's going to have a much higher force required to get it to displace by a certain length, right? Does that make sense? A thicker, bigger part, it's going to be stiffer, more rigid. It's going to take more force to get it to stretch by a certain amount. So this is the data as you could plot it as it comes out of the Instron machine. This is your raw data. But the problem is that this data is extrinsic. It depends on the specific part that you're testing. And that's a problem because we might want to use a totally different shape of parts to go design a beam or a chassis, structural element, something like that. So we need to get intrinsic data. So we take our load force in pounds force. This should be pounds force right here. Pounds force divided by the cross-sectional area of the part to give us stress. And we take the displacement in inches and divide by the original length. So this is the change in length. We're going to divide by the original length to get the strain. So you'll notice that the curves actually look the same. Your curve for load versus displacement looks the same as your curve for stress strain. But the difference is this is extrinsic data that's not really very useful to us if I want to go design some other part out of that same material. But this is very useful for us. This is intrinsic data because now I can use this data and I can go design some other part that's a totally different shape using the things that I find out about this material. All right, so this curve in blue was obtained by dividing each and every one of these load data points by the cross-sectional area and dividing each one of these displacement data points by the original length of the specimen. And that gives us strain down here. So this is what we call a stress-strain curve down here, and you're going to see a lot of them in this class. This is an extremely important concept in this class, how to create and read and interpret stress-strain curves. And this is what I just said. Stress is load force divided by area. Strain is change in length or displacement divided by the gauge length, which was that original length of the specimen. All right, so this is just a blown up curve of the stress strain data for the curve. And we're going to have some important regions. Let me just point them out right here before we go on and talk about them. But notice a couple of regions here. First of all, in this area right here, the curve looks pretty close to linear, like it's almost a straight line. All right, and it is actually. It is very close to a straight line. That's what we're going to call the elastic region of the stress strain curve. And then we get to a point somewhere probably around here, somewhere around here, where it's no longer linear. We lose the linear region of the curve, and now it becomes nonlinear. There's a name for this point where it stops being linear, and that's called the yield stress, Y-I-E-L-D, the yield stress for this curve, or the yield point. And then, of course, we have the peak up here that is the very maximum amount of stress that you can see for this material. And that we're going to call the ultimate tensile strength or ultimate tensile stress. And you already looked those up for lab 1, the very first lab. But now we're going to talk about how we actually get those numbers. And then the last important point over here is when it ultimately fails. So we can call that the failure stress. I'll go ahead and point out there's a notch right here. It seems kind of weird, but there's a very good reason for that notch being there. It's not really related to the material itself. It's related to how we test the material. And we'll talk about that in a few minutes. Here's another example of a stress strain curve. This is a type of plastic. And so you can see the values are different. You know, this is a type of plastic, and the ultimate tensile strength is somewhere just under 5,000 psi. Whereas going back a slide, this was 1018 steel, and its ultimate tensile strength looks like it was somewhere 93,000 psi. So you can see the values are going to look different, and the shapes look a little different too. But you're pretty much always going to see some kind of linear region right here. You're going to see some point where it's no longer linear, around right there, and you're going to see some peak in the curve. So here I'd say the linear region is right around here. The yield stress, where it stops being linear, is probably somewhere around right here or so. And the ultimate tensile strength, that is the peak of the stress curve, is obviously about right here. All right, it's going to be really important to know the dimensions of the part. So for the next couple of labs, you'll have to make sure that you know the dimensions. And I could have you measure these in the lab, but I think I'm just going to tell you what they are. So when we come to that, I'm just going to tell you what these dimensions are so that you can then calculate the stress and the strain. You need to know the cross-sectional area to calculate the stress, and you need to know the gauge length, which is this dimension or this dimension, in order to calculate the strain. Now let's talk a little bit more about calculating strain, particularly. So we know that strain is equal to the change in length of the test section right here, divided by the original length of this test section area right here. So the original length, that's this length right here, also called the gauge length. We can measure that. And now let's talk about how we measure the change in length. How do you get that data? You know, it's going to be spit out by the computer, but how does that computer even get that data for the change in length? So there's actually 3 different ways that are allowed by the ASTM instruction to measure the change in length of the part that you're doing tensile testing on. The first way is the way that I've kind of alluded to so far, and that is to say that, all right, our section, our test section is going to be this narrow length right here, and I'm going to assume, because it is kind of an assumption, it's a decent assumption, but we're going to assume that any movement of the moving crosshead of the machine results in a stretch of that same amount in the gauge length section of this part. All right, so we could make the assumption that if the moving crosshead of the machine moves by 1/4 inch, then this section right here has stretched by 1/4 inch. All right, so that's a bit of an assumption. It's usually a pretty decent assumption, but not always. It's not always. So this is to say that any displacement of the crosshead, the moving crosshead, I should say, the moving crosshead results in stretch of the gauge length of the part. This is the easiest way because this is what's naturally spit out by the machine, the UTM machine, and it's pretty simple and straightforward. So the UTM machine measures the rotation of that lead screw, and as that lead screw rotates, it causes the moving crosshead to move up and down, and any movement of the moving crosshead up or down causes a deformation in the test section of this part right here. All right, so if we use this method, then we can use the displacement data directly from the UTM machine itself. So it's pretty easy and pretty straightforward. But the disadvantage, and there are actually a couple here, that's an assumption. It's an assumption because there are a couple things that could be happening. First of all, you could get some stretch in these thicker sections of the part. The reason why the part is designed like this, it's designed so that it has a thinner section right here, or like this one is the same way. It's designed so that it has a thinner section to guarantee that most of the stretch of the part is going to take place in this thinner section right here. Why will it do that? Well, because if you think about the stress values, the stress is much higher in this area here than it is in these thicker sections right here. However, That being said, you still will get some small amount of stretch in the thicker sections of the part. And so it's not zero. You still get a little bit of deformation in the thicker sections of the part. And another reason is that particularly if you're testing metals or anything that has a very high elastic modulus or a high ultimate tensile strength, either one, what can happen is that the moving crosshead itself can actually bend. It actually will. Not only can it, it will. It will actually bend imperceptibly to us. You're not going to be able to look at the moving crosshead and see that it is bowed, but it is actually. It is a little bit, and it's enough to affect the data. And so this is a pretty good test method when you're using plastic materials and materials that have a relatively low strength value. But for metals and strong materials, it's not the best method of measuring the change in length. There is a second way that is allowed by, actually there's two more ways, but the second way we're going to talk about that is allowed by the ASTM procedure. It seems kind of silly and kind of crude, but it's actually allowed. What you can do is take a Sharpie marker or a pencil and make a mark, say right here on the specimen, and make a mark down here on the specimen, and then measure that length. And then periodically, as you're doing the test, stop the test and measure the new change in length. And then run the test again for a few more seconds, then stop the test, and then measure the change in length again. So you can make scratches on the test specimen, or you could use a punch to make some small marks on it. Or like I said, use a Sharpie marker or a pen or something and make these marks. And then periodically stop the test and re-measure the length to get the change in length. The advantage here, obviously, is it's super simple to use. Even if you're using a really simple test measuring equipment, you can use this method. The disadvantage here, obviously it relies on human measurement, so there's opportunity for human error in there. And the second thing is that it's not continuous. You have to stop the test to re-measure the length and then run it again, then stop it. So you're not getting a smooth, continuous data stream. You're only getting these periodic data points that happen, however often you want to stop the test. But there is a third option, and this is actually the best option, especially when you're dealing with pretty strong materials. And this is what we're going to use when we do the tensile tests on metals in the next couple of labs. What we're going to use is called an extensometer. And an extensometer is a small piece of equipment, and I actually have it right here. Normally I would pass this around in the class, but we can't do that. So what we have is an extensometer right here, and you can see that it has some clips right here. So the way this works is, first of all, you load your specimen in the grips of the machine, and then you take the extensometer and you push these buttons together, which sets the initial distance of separation between these two clips. And then you attach these clips to the specimen just like that. I'll do it from a different angle so maybe you can see a little bit better. So here's our specimen that's loaded in the machine, and then you put the extensometer inside those clips like this. And then you gradually let go of the button. And now that machine, the extensometer, is exactly at a now it's not supposed to move around like that after you do it, but now the machine knows exactly what the initial separation distance is between these clips. And then as you're running the test, of course, this stretches, and these clips move along with the part as it's being stretched. And then the other end here plugs into the Instron machine, and it records the data just like it would if it was using the encoder from the screw, the worm gear screw. All right, so this is the most accurate method because for sure, the only length that's being measured as it's being stretched is this length right here between these two clips. So it's definitely not going to be impacted by the stretch of these parts of the specimen, and it's definitely not going to be impacted by any potential bowing or deflection of the moving crosshead. And another good advantage is that it is still automatically recorded by the computer. You don't have to stop the test and record it yourself every couple of minutes. But the downsides here, well, you got to purchase another piece of equipment. All of this stuff, all these attachments for that machine are really expensive. I don't remember how expensive this one is in particular, but I'd be willing to bet it's well over $1,000 just for this extensometer and the clips that come with it. The other thing is that extensometers are pretty fragile, and in fact they are so fragile that we're actually going to stop the test and we're actually going to remove the extensometer before the specimen breaks. So we'll talk about this when we talk about the next lab, but what we're going to do is we're going to attach the extensometer to the specimen, and then we're going to run the test up to a certain point, and then we're going to remove the extensometer, and then we're going to continue the test using the first method that I talked about before, which is the moving crosshead method of measuring the change in length of the specimen. All right. If that's not quite clear yet, don't worry. We'll talk about that when we talk about doing lab 4. Okay. All right, so once again, here is a stress strain curve, and here are a few points on the stress strain curve that are labeled, and a few regions that are labeled. So first of all, this linear region right here, I mentioned this before, but this is called the elastic region. And that's because in this region, we're getting elastic deformation. So if you were to stretch the part, say up to here, and then release the part, let it go, it would go back to its initial shape, just like a spring. And we know that because we've got elastic deformation. Elastic means temporary. Once you get up to here, this is called the yield strength or the yield stress. Once you get beyond that, this is called the plastic deformation region. In fact, this is called the uniform plastic deformation region because the whole test specimen region is deforming plastically, but uniformly. And the reason we call it uniform deformation is because once we get into this region, it's not uniform. Specifically, what you get is something called necking. And necking is not uniform. Necking happens locally at a certain point, at the weakest point in the specimen, where you get a rapid localized reduction in the cross-sectional area of the specimen. And then eventually it's going to fail right there where it starts necking. So that necking occurs right around the points of the ultimate tensile strength. This point right here is the ultimate tensile strength, and after that you start getting necking, and then eventually you get failure right here. So you should know these different points of the curve. You should know the yield strength. You should know the ultimate tensile strength. You should know the failure strength. And you should know these regions are the elastic deformation region, the uniform plastic deformation region, and the non-uniform plastic deformation region, which is characterized by necking. So here we've got elastic strain, here we've got plastic strain. One important thing to note is, let's say I did this test and I carried out this test all the way up to here, and then I released the part. What would happen? Well, we have a lot of elastic deformation and we have some plastic deformation. So what's going to happen is you're going to recover the elastic part and you're not going to recover the plastic part. So what's going to happen if you release it, it's going to come back along this line right here. Come back along that line right there, which has the same slope as the elastic region right here, right? It has a certain slope and it comes back along that same slope and it ends up right here. So notice it will not end up with the same length because this is a change in length right here, right? So it has some change in length, so it will not go back to its original length when you release the part. There are a few terms that I've been throwing around here in the past few minutes, and let's go ahead and define them more thoroughly. First of all, we have the elastic modulus in tension, because it will have a modulus in compression as well. But for now, we just have the elastic modulus in tension, otherwise known as the Young's modulus. What this is the resistance to stretching. If you have a high elastic modulus, then it's a stiff part. It has a resistance to stretching. And now the measurement, quantitatively, the way we measure that, it's equal to the slope. It's actually the slope of that linear region of the stress-strain curve. So the way you would calculate the elastic modulus is by selecting 2 points on this linear region right here. Say a point down here towards the bottom of the linear elastic region and a point up here close to the yield stress. And then look at those 2 points and calculate the slope between them. Remember that slope is rise over run. So the rise is the difference in the vertical values here, the difference in the stress. And the run is the difference in the horizontal values, which is the difference in the strain, right? So you take these 2 data points and you take the difference between the stress values, divide that by the difference in the strain values, rise over run. All right, so this applies only in the elastic region. You can't talk about the elastic modulus in the plastic region because it's not applicable. It doesn't work. You only have the elastic modulus in the elastic region. This is the part of the testing that works like a spring. And every material has an elastic region, and every material has an elastic modulus in that elastic region. So this is the part that works like lab 2. Then we get to the yield strength. The yield strength, as I mentioned before, that's the end of the linear elastic region. So we no longer have elastic deformation, we start plastic deformation. And we measure this either in PSI or KSI. KSI is 1,000 PSI, but 1 KSI equals 1,000 PSI. Or if you prefer the metric system, then pascals, which is a Newton per meter squared, or megapascals, which is 1,000,000 pascals per meter squared. The next term to be familiar with is called the ultimate tensile strength, which we abbreviate with a sigma subscript U. The U stands for ultimate tensile strength. Whereas we also had sigma with a subscript Y before, that stood for the yield stress or the yield strength. Now, the ultimate tensile strength, this is the peak of that curve, so it's the maximum stress that a material can withstand. We measure it in PSI or KSI or megapascals, so it has the same units as yield stress or yield strength. And when we have a material that reaches the ultimate tensile strength, of course, we're beyond the yield stress now, so we are going to have both elastic and plastic deformation in that part. And usually, right around or right after the ultimate tensile strength, that's when we start getting necking in the material. I think this is a good time to pause and stretch a little bit and get your blood moving a little bit. As I mentioned, the elastic modulus is simply equal to the slope of this linear region right here of the curve. And the slope is equal to rise over run. So when you select 2 data points in the linear region right here, you take the difference in the stress values between those 2 points and divide by the difference in the strain values, which is the run or the horizontal values in that equation. So this is what your equation looks like, the change in stress between those 2 data points that you select divided by the change in strain for those 2 data points that you select. Here's a little bit of a tricky thing, and that is the units for the elastic modulus. So look at the units for stress or PSI typically, And the units for strain are inches per inch. See down here, inches per inch. So remember what strain was. Strain was change in length, which is inches, divided by original length, which is inches. So strain is usually measured as inches per inch, or inches of change in length divided by inches of original length, all right, inches per inch. So our modulus value, elastic modulus E, change in stress, that's PSI, divided by change in strain, inches per inch. However, for the purpose of stating the elastic modulus, this is just a convention. I don't know how this started, but the convention is to say that in the denominator, the inches per inch, they cancel out. And so your units for elastic modulus are simply PSI, right? That's the way you'll always see it. If you go on matweb.com or look up in any materials textbook, the units for elastic modulus are always in some unit of stress, whether it's PSI or KSI or pascals or megapascals. It's going to be some unit like that. So for our purposes, you'll put them in PSI. So for this calculation, if you had this curve, you could pick a point right here. Say that's one of the points you'll use to calculate the elastic modulus. And if you draw a straight line down, it doesn't actually matter whether your point is on that curve. It just has to be on the extension of that curve, because you're just trying to calculate the slope of that line. So to calculate the slope here, we've picked this point right here, which is an extension of that linear region, and this point right here. So the change in stress is 80,000 psi minus 0, and the change in strain is 0.03, which is right here, minus 0.01, which is right here. So 80,000 psi divided by 0.03 minus 0.01 gives you 4 million psi. Note down here it says that the units for elastic modulus and yield strength and ultimate tensile strength, they're all the same. They're all in psi, but they mean different things. So be careful there, especially with the units for elastic modulus. All right, here's a couple more examples. Here's the ultimate tensile strength for this material. Here's about the yield strength, about 80,000 psi for this material. The fracture strength is something you'll label in your labs. So over here, it's about 68,000 psi. And the elongation, that's how much the material elongated during the test. And usually that's put in a percentage, and it's equal to the strain value at the maximum elongation of the material. So when it had a strain value of 0.21 inches per inch, that means it's stretched or elongated by 21%. Here's a little bit more about toe compensation. And this you will see sometimes, maybe even a little bit in our labs, probably not to an extreme value. But here's how you could get some toe compensation. So what can happen over in this region, right when we start the test, we're going to put our specimen in the grips. But then as you start the test, there could be a little bit of wiggle or some kind of slop in the fixture that gets tightened out of the fixture right away when you start the test. And so that's why you could get some strain with very little stress initially, is because you're pulling out any kind of slop or wiggle room in that test fixture. So that's why we try to tighten it up as best we can in those grips and in the test fixture. But every once in a while, all the same, you will see some toe compensation in your plots. So when you do that, just kind of ignore this area. This is not part of the linear elastic region. The linear region is this part right here. So don't pick the origin as one of your points to calculate the elastic modulus if you're seeing some significant toe compensation like this in your plot. Here's even worse. I don't think you'll see any toe compensation nearly this bad in our labs, but if you do see toe compensation and you're going to go calculate the elastic modulus, just make sure you only use the linear region here to calculate the elastic modulus. Here are a few different curves. So this is 1018 steel. Here's a stress strain curve for 1018 steel. And here's a stress strain curve for polycarbonate, a type of plastic. So you can see that the stress strain curves look very different for steel versus plastic, which you might expect. And you can also, from these stress strain curves, tell that steel is a heck of a lot stronger. You know, the ultimate tensile strength for steel is way up here at 93,000 psi, whereas the ultimate tensile strength for polycarbonate was way down here at about 9,000 psi. However, if we talk about ductility, or the maximum elongation that the materials can get, looks like polycarbonate is way more ductile than 1018 steel is. So the elongation at failure for the polycarbonate was way over here at like 0.78 or 78% elongation at failure, whereas the 1018 steel was only maybe 0.22, 22% elongation at failure. So when we want to calculate the elastic modulus for these two materials, if we want to do the 1018 steel, again, we can extend this linear line up here, and we extend it up to 100,000 if we want to. You could just pick 2 points, say here and the origin if you wanted to, but here, arbitrarily, I extended it up to 100,000. And at 100,000, if we drop a line straight down, we'd get a strain value of about 0.03. So the slope of that line is 100,000 minus 0. That's the change in stress. And the strain is 0.03. That's right here, minus 0, which is at the origin. That's the change in strain. So I do that math right here, and I get a value of 3.3 million psi for the elastic modulus for 1018 steel. For the polycarbonate, I do a similar thing. Just to make the numbers a little bit easier, I extended this linear region out to here, and I find that I would get 40,000, and if I drop a line straight down from there, I'd get 0.7. So if I take the change in stress divided by the change in strain, you'd get about 57,000 psi. I want to reiterate that you don't have to extend this line out here. In fact, in your labs, it's probably easier not to. If you want to calculate the elastic modulus in your labs, it's probably easiest just to take 2 points somewhere on your linear region, your linear elastic region. Try to get those 2 data points separated by as much space as possible. That will give you a more accurate reading. But that's probably the easiest way, is to pick 2 points in your linear elastic region. One, say, up here, and one down here close to the origin. If you don't have toe compensation, you can go at the origin. You can pick that for one of your points, but you don't have to. All right, there's our ultimate tensile strength for our 1018 steel, and there's our ultimate tensile strength for the polycarbonate. One of the last things we'll talk about is ductility. Ductility is the ability of material to undergo plastic deformation before it fails. And we usually just measure that by saying, well, what was the strain or what was the elongation when it failed? All right, so that is a measure of ductility. The opposite of that, if it's not ductile, then it could be brittle. Brittle means it exhibits very little plastic deformation before it just fails. So it snaps. It fails pretty abruptly if it's a brittle material. Here's an example. So this red curve, notice how it got up to the yield stress, probably around there. This is probably around the yield stress. And then there was very little additional plastic deformation before it just snapped, it failed. So this red curve represents a brittle material, whereas this blue curve, okay, the yield stress is probably around here, and they had all this plastic deformation right here. So you'd say that's a pretty ductile material. If you looked at these parts after they failed, you would see that the ductile material in blue likely had a fair amount of necking right here. So you can see that localized reduction in cross-sectional area right there. So that's what you get when you get a lot of plastic deformation. If it's brittle and you don't get much plastic deformation, then you don't get much necking. Notice how the cross-sectional area here is pretty close to the cross-sectional area way over here. So if we go back to the curves we just looked at a slide or two ago, we could say, all right, the ductility here, drop a line straight down here from where it failed, and you'd say the ductility is about 21%. And over here, it failed right here at a strain value of 0.78, so you'd say the ductility is about 78%. A good example of a material that's pretty brittle is cast iron, and we'll talk more about that in a later class session when we talk about ferrous metals. But cast iron tends to be quite brittle, and when you do a tensile test on a brittle material, you don't see very much necking. So if you look at this specimen right here and here, right, this specimen here, you don't see a reduction in cross-sectional area. It's pretty much just the same where it failed. So that is a characterization of brittle materials. The last concept that we'll talk about today is called tensile toughness. Now, toughness in general terms is the ability of a material to absorb energy before failing. So tensile toughness is the ability of a material to absorb energy in a tensile test before it fails. And the way that you can calculate the toughness of a material in a tensile test is by calculating the area under that stress-strain curve. So if you want to get a tough material, you're trying to maximize the area under that stress-strain curve. And if you're trying to maximize the area under the stress-strain curve, then you want to have both the vertical and the horizontal dimensions be pretty large. So if you want to maximize the vertical dimension, then your material needs to be at least fairly strong. And if you want to maximize the horizontal dimension, then your material needs to be at least fairly ductile. So if you have materials that are simultaneously at least moderately strong and at least moderately ductile, then you're going to maximize and have a fairly large area under the stress-strain curve, and you would say that's a pretty tough material. I'll show you a few examples. So here's an example I've showed before when we talked about brittle versus ductile materials. But if you think about the area under these curves, which one do you think is going to be a tougher material? Well, the tougher material has the larger area under the curve. Clearly, the blue curve has a larger area under the curve than the red specimen did. So obviously the blue curve represents a much tougher material than the red specimen or the red curve did. So using the terms that we've described so far, we can look at these stress-strain curves. There's 4 of them, here and here and here and here, and we can talk about the characteristics of those materials. So if we took a specimen and we did a tensile test and we got this stress-strain curve, what could we say about that specimen? Well, we could say it's pretty ductile because it was pretty stretched out in the horizontal dimension, which meant that it had a large strain value when it failed. So that means it's ductile. And we could also say that it's at least moderately tough because it has a pretty large area under this stress-strain curve. This curve right here, the second one up from the bottom, we could say that it's pretty rigid or stiff. It has a high elastic modulus. Why? Because the slope of the linear elastic region here is pretty high. It has a pretty high slope right here. We'd also say this is pretty tough because it also has a pretty large area under this stress-strain curve. This third one we'd say is also rigid or stiff because it too has a large slope here for the linear elastic region. And we'd also say it's strong because it could withstand a very high stress before it failed. So the ultimate tensile strength here is the highest among all these specimens. So we'd say this is the strongest specimen of these 4. And this last one here, well, it's rigid and stiff because it has a very steep slope right here, so it has a large elastic modulus, but it had very little to no plastic deformation, and so we'd say that it was very brittle. All right, I think that's going to wrap things up for today. I'm gonna stop here for today. And in the next class, we will talk about true stress versus engineering stress. We'll wrap up this presentation, and then we'll start talking about how to do some calculations for tensile testing in the next couple of labs. So I think I'm going to stop this video here for today. Have a good weekend, and I'll see you next week.